So this is based on joint work with Jaume Martí Ferrer and José Luis Ruiz, which are my colleagues in Barcelona. So basically, I want to tell you how a question that Jaume had like 5 years ago with time ended up having a quite simple answer. Or now it seems simple to us, at least. So let me start with that. So it's about clutters. And a clutter, by a clutter, I mean a family of sets that are mutually incomparable. So an antichain of subsets, of finite set, and always. So it's always going to be finite. So no subset of the clutter is, or no element of the clutter is contained in another. And so, like this audience, if we think of clutters, we can think about the circuits of a matroid are a clutter, and the bases of a matroid are a clutter. If you want, the hyperplanes are also a clutter, the rank K flats. And in other contexts, my co-authors were interested at some point in dominating sets in graphs. And Jaume was also interested in matroid boards. And the question he had was, okay, I have a clutter which is not of the family I like, in this case not a matroid clutter, which is, say, the matroid that's closest to lambda. And this is quite, so I have a clutter which is not, say, a circuit clutter. Can I find a matroid whose circuits are close to lambda? Or same with bases or with any other matroid clutter you like. So here's like an example with that clutter with 3 elements. And so this 1 to 3 means the set 1 to 3, but I don't write brackets or commas because to make things easier. So these 2 matroids are clutters of circuits of a matroid. Sorry, these two clutters are clutters of circuits, and they somehow resemble the first one. They should be candidates to being close. It's not going to be as easy as just to add elements to the clutter. I mean, we'll have to remove, to break, to add. So this would be like 2 clutter matroids that are somehow close to the first one, or if instead of thinking about circuits, we want to think about bases, we could have these 2. Removing 1 element from lambda gives already a clutter of bases, and otherwise we can also add a few elements to lambda and get another clutter of bases. Okay, so before getting into the way we approach this question, these are sort of efforts that I found in the literature about linking these ideas of clutters and matroids. And basically, except for the second one of Dress and Wenzel, they actually start with a clutter and they try to construct a matroid from it. All the rest are more about properties that clutters and matroids have in common, or how clutters behave like matroids in some sense. So there's been some interest in linking this, in thinking about clutters and matroids, but really we couldn't find anything that was similar to that could answer that question. So our setting is the following. So clutter of omega is just all clutters on omega. And so I have my clutter lambda. And from this clutter, we'll define two families of sets. One is like, we can say, the ascending family. So all lambda plus is all sets that contain at least one element of the clutter, and lambda minus, it's like the descending chain or the descending family, all sets that are containing at least one element in the clutter. So the clutter is, so multiplied clutter is the minimal of the plus and the maximal of the minus. So for instance, if we are in matroids, circuit plus is just all elements that contain a circuit, so it's all the dependent sets. Basis minus would be all elements that are included in a basis, which will be independent sets. And we use this lambda plus and lambda minus to put an order to clutters and to just try to see what do we mean close, that two clutters are close. And we define these two partial orders. Basically, the order plus is just the plus families are included the first in the second, and the order minus is the minus families are included the first in the second. Here it's written what it means. So lambda plus amounts to every element of the small clutter contains an element of the second, and the order minus is every element of the small clutter is contained in an element of the second. And they look a bit different, but they are related. And there are two operations on clutters that basically allow us to switch to one order, from one order to the other. And one is just the complement, it's just taking the complement of each of the elements of the clutter. And the other one is the blocker, which is also a well-known operation on clutters, which we take all sets that intersect all the elements of the clutter, and then we take the minimal of those so that the result is a clutter. And it's clear that the complement of the complement is just the original clutter, and it's also true that the blocker is involutive, so the blocker of the blocker is itself. And now these operations of complementary and blocker, they behave well, let's say, with respect to the orders. So the complement switches from one order to the other by keeping the relative position of the elements. Sorry. And the blocker just in the plus order just moves things around. And if you want to move things around in the minus order, well, you go to the complement, you go to the plus order, to blocker, and you go back. So basically, everything we could say with the plus order, we can say it for the other, just moving, just with blockers and complements. And these complements and blockers, if we specialize to matroid clutters, basically, if you think of it, they are just duals. So this H is the set of hyperplanes. So sure, you can easily fill this table. The complement of the bases are the co-bases, and the blocker of the bases turn out to be the co-circuits, and so on. And these orders for circuit and basis clutters, they basically are rephrasings of the weak order, except that the order minus for circuits has no particular meaning that I know in terms of weak orders or similar. So, like if we are thinking of clutters with the plus order, then this order is extending the weak order. So this order restricted to circuit clutters is the weak order. Okay, so what's the setting? So we have our clutter lambda, and we want it to be close, or to see which are the circuit clutters that are closer to it, or the basis clutters, or hyperplane clutters, or any family of clutters. So we'll have a family sigma, which are our target clutters, that they don't have even, the motivation was sort of matroid clutters, but they could be just any family of clutters that we like. And then we are going to choose in which order do we want to compare, in the plus or in the minus. So we'll just take one of those, let's call it order. So, and finally, I have my clutter here, and here's my order, and I would like to know the clutters that are just above it in my family sigma in this order, or just below it. So I will choose one side. I want to approximate from above or from below. And the sort of theorems we have, which stated informally, is that if you choose any of the orders and either of the sides, there's going to be a family of clutters, a fixed family of clutters, that's called F, and sometimes I refer to it as the special family, such that if my target family sigma contains F, then there are some clutters in sigma that are the closest to lambda with respect to that order and side, and that's pretty easy, that's almost straightforward. But the part that I found more interesting is that once I have these closest clutters to lambda, then lambda can be recovered from this by some operation. So I like to think of it as a sort of factorization, that I can write lambda in terms of the elements of sigma and in terms of the elements of sigma that are closest to lambda. The problem is that this sort of factorization is not unique, but well, at least I can recover lambda from those. So in the particular, so this is the particular statement for the order plus and approximating from above. So it says, so it says, for any set of elements, I consider the clutter which is just made of singletons. So just that set of elements made of singletons. And then if my family sigma contains all of these, then indeed there are elements of sigma just above lambda. And if I take the minimal that are just, the minimal in sigma that are just above lambda, my original clutter lambda can be written in this form. It's you take all the ascending families of all these lambda 1, lambda s. We take all the intersections, and then we take the minimal ones to get a clutter. And that recovers lambda. So the proof is even of the second case is not very complicated. The first one is just there to, I mean, it's almost clear. It's very simple to see that this lambda prime above lambda exists, but these elements above lambda are the ones that give us the factorization. So basically, using blockers and complements, then once one has one of the cases, all the others just are immediate. So what we end up having is, for each combination of order and side, we have this family F, whatever, plus upper or plus lower, whatever it is, that if I contain this family, then there are some elements in the target class sigma that are the closest ones, and I can recover my clutter from those. And the operations that give us the original clutter are just unions and intersections of family of ascending families or descending families. So, and this is in general for any family sigma of target clutters. And once we says, okay, and what about for matroid clutters? And if you look at all these families F, you'll see that all of them are clutters of bases of some matroid on omega, and all of them except one are clutters of circuits, and the one that's not clutter of circuit is the third one. So if omega is at least 4 elements, I think, or even 3, that family, that clutter doesn't satisfy a circuit elimination, so it's not a family of clutters. And actually, these are also clutters of bases or circuits, except for that. If instead of you want all circuits, one would like circuits of graphic matroids. So I want to approximate by matroids, but just graphic matroids, or just binary matroids, or just representable or transversal, or almost all your favorite classes. It's going to work the same. Okay. So in summary, if I just restrict to the circuits basis case to keep things simple, so given a clutter lambda, we can do these approximations for any combination of circuits or bases, either order or above or below or upper or lower, except circuits order minus and upper. And for that case, it is easy to see that there are non-circuit clutters that are covered just by one circuit clutter in the order, so it's impossible to recover the bottom one from that one. So another thing, so this was just an existential result, but now what we also ask is, okay, can we find these clutters? They theoretically exist, but how do we find them? And basically by combining blockers and complements and so on, we only have to solve one on each of these 3 groups. And basically what we did was to give algorithms for the circuit cases. So the first one was given by Jaume in his, like 4 years ago. And then we did the other two. And I won't go into the details, but they are based on this idea that so if I have two elements of a clutter A1 and A2, I define this, what we call this sort of intersection, which is intersect all elements of the clutter that are included in the union of A1 and A2, and that's going to be some set. And then it turns out that if the clutter is a clutter of circuits, this intersection I lambda is going to be empty for every pair of elements. It's an easy check. So basically, what our algorithms do is to go over to go repeatedly over the clutter, look at pairs of elements for which this intersection is non-empty, and then try to just remove elements or add elements to force all these intersections to be empty. And so somehow brute force. You keep applying rules and rules and rules, and when no more rules can be applied, then it's that we reached. Then it means that we've reached circuit clutters. And basically, it's the same idea for all three with some modifications. And it turns out that we can do it for circuits, but I have no idea how to do it with bases without using blockers and complements and so on. And using blockers is not, I mean, these algorithms are not very good. And if in addition you add, well, not very fast, I mean. If in addition you add blockers to it, which are hard to compute, it's going to be worse. So really we have no idea how to start with bases directly. Okay, so I said before that we ended up having an easy solution to our problem, and not that theorem was very difficult, but actually we learned not so long ago that, or we realized that we were just dealing about results in decomposing elements in distributive lattices. So if you go back to the operations that we had in each cases of how to recover the clutter from the approximations, the operations ended up to, well, they were like this. So the minimal of the intersection of the ascending chains, or the minimal of the intersection of the union of the ascending chains, and so on. So we call them intersections plus or intersections minus. And it turns out that both sets of clutters with the order plus or the order minus are distributive lattice with these operations of plus union and plus intersection. So I have, well, it's a bit small, but these are for 3 elements. These are how the clutters look like. So it's, of course, it's the same clutters, but arranged in a different way. So now if we look at those families of clutters that had to be included in sigma in order to get an approximation and this sort of factorization, it turns out that those families were just the joint irreducibles or the meet irreducibles in that lattice. So, and then you go to lattice theory books and they tell you, yes, of course, if you've got all joint irreducibles, you must have this decomposition. So these are the, I don't know what I did here. Sorry. I lost, no. Okay. So these are the meet irreducibles, which will be for the up approximation. So those ones here on the left are the ones that are made just of singletons. And that, and these are just the corresponding ones in the minus lattice. Okay, so at the end, the theoretical part was just checking that the family contains the joint irreducibles or the meet irreducibles according to what we want, but then it's still quite then there's also the problem of how to find them. That's another story. But at least existence is granted for that. So then we went to another variation of the problem, which is to fix the ground set. So they say, okay, now I want, so and this maybe with the motivation that Jaume and Jose Luis had from dominating sets in graphs was more natural. I want every element to appear in at least one element of the clutter. So I don't want to have like dummy elements. So here in red are the clutters, such that the union of the elements is the whole ground set. And now I want to approximate, I want to restrict to the red clutter. So I want one of the red clutters, and I will have some family of target clutters there, and I want to approximate these red clutters by the others. And then if you look at the order minus, you see that the red ones are just a sublattice of the big lattice. And one can prove that that's the case. It's a sublattice with the corresponding operations. So for that one, it's just the same story. Find the meet and the joint irreducibles, and that would give you an analogous theorem. But on the other side, well, this one is small. And if you look at the red elements, you see, okay, they are not a sublattice with the operations, but there seems to be, if you just define this bottom red to be the meets of all these three, that could work. But that's just because 3 is small. But if the next one has like 168 elements, so I wouldn't dare to draw it. But the next one is not a lattice. So the minus, even if we fix that the union of the elements of the clutter is the whole ground set, it's a lattice. But the other one cannot be made a lattice. So if you want to decompose, to do the analogous thing with the order minus, just the same, look at the joint irreducibles or the meet irreducibles, and they are easy to find. I just didn't write them down to save space, but just do it. It's easy to do. And the nice thing is that for the other, which is not a lattice, there's still the same statement. So it's again, if I have a target family in the clutters with fixed ground set, and I want to be able to decompose with respect to that family with the order plus, there are some family of clutters that I have to have in my family. And if I have those, then everything works as before. And if I don't have them, then I cannot do it. Okay, so this is sort of the analogous result. For this one, we don't have yet a way to find this, how to find this smallest clutter. So we know they exist, but the algorithms we have, they don't maintain this property of having of the union of the clutter being the whole ground set. So we need to devise new algorithms. So that's where we stand at this point. So I'll end here. Thank you.
Okay, thank you. Questions? Okay, so let's thanks again. There is one question over there.
Okay. I was just wondering, I mean, here it looked like you take the Boolean lattice and the antichains, and then you go to this subset lattice of it for the clutter. Oh no, you take the antichains and the subset lattice of the Boolean lattice. And I was wondering if you can also look, instead of the Boolean lattice, maybe at a distributive lattice or something like that, to get like discrete polymatroid generalizations of what you were doing. Right. Maybe some things of it would work in a similar way.
So like we had the set of, I'm not sure if I was following you, but so we have this set of all the clutters, and we have like two ways that look natural to us to order them, but maybe there are others and we haven't looked at. I don't know. Okay. So like this plot was like the more natural thinking about circuits, and then the other was natural thinking about bases, but I don't know if there are other options.
Thank you.
Question? Are you sure? Now we can see the answer.
Thank you.
Okay.